So hi everyone, I am Dr. Sachidanand Sen, working as Associate Professor in the Department of EEE, SR University Warangal, and we are continuing with our lecture series on battery management system. And today is the 8th lecture, and we are going to see on the topic of battery aging and life cycle management. So let us briefly understand what is this effect, what is this aging effect, and what is this life cycle, how we are able to extend the life cycle, what are the factors that will be depending or deciding how the life cycle of the battery will come out to be. Okay, so first of all, definition will be the battery aging refers to the gradual loss of capability. So with passage of time, as the charging and discharging cycles continues, so definitely there will be some loss in the capacity and power and efficiency over the time. Then it's like normally as a human being also, as aging comes, our body's functionality gradually degrades with time. Same way, any battery or any machinery, they lost their full efficiency. Okay, it won't be able to perform at the best possible scenario. Okay, so some losses will be there in terms of capacity, power and efficiency. Then life cycle management. Life cycle means management means monitoring, continuous monitoring of the operations of the batteries, then controlling and optimizing the battery's performance across its usable or operational life. Okay, so monitoring, control and optimization. Okay, so these things are called life cycle management. How we can extend the functionality of the batteries for longer duration, as long as possible. Then comes why the battery aging effect is important. Okay, so why aging matters in electric batteries? So it determines the driving range, charging time and vehicle warranty. Okay, so how long the vehicle will run, okay, how much time it will take to charge, then how long the vehicle's warranty will be there, means that some replacement can be done, okay, 3 years, 5 years. So depends, all these things depend upon the functionality of the batteries. So any EV manufacturer, okay, which designs the batteries at least for 8 to 10 years, okay, or at least 1500 to 2000 full cycles. So any battery which is being used in electric vehicles, they are expecting to for 8 to 10 years of running. So like normal diesel or petrol vehicles also, at least around 10 years of running is expected from them. Same way the battery in the electric vehicle, the first thing that will be degraded will be the battery. So battery will decide how long the electric vehicle will be used. Okay, so expectedly the manufacturer will be going for at least 8 to 10 years of operational life of the battery. So aging effect, so how it will be affecting state of charge, state of health, okay, remaining useful life, these things need to be estimated. Okay, these are the important parameters which we have already discussed in the previous lectures. Then typical life cycle stages. So what are the basic stages of a battery? Okay, first stage is formation and early life. At the beginning, first time we are charging that one. Okay, first few charging cycles. So here what happens? The stabilization of solid electrolyte interface layer takes place. Okay, so this is the task being done within the first 100 cycles. Then nominal operation between 100 to 1000 cycles, the degradation will be slower, and beyond 1000 aging effect will kick in. Okay, it will create gradual degradation in the performance, faster capacity fade and internal resistance will increase. I hope you can recall from the previous lecture that during the state of health I have mentioned that internal resistance will increase and capacity will decrease. The storing energy storage capacity will be degraded. So these are the two effects that will come as the battery is facing the aging effect or aging acceleration. Then end of life. So once the battery storage capacity is going below 80% of the initial capacity, then we are not considering that to be suitable for use in electric vehicles. So definitely we will consider that battery to be replaced and that battery can be used for second life like stationary power systems, okay, for microgrid, renewable energy integration and all. Different applications are also possible for second life cycle, but not suitable for electric vehicles because our life continuously depends on the performance of the battery and the motor, and that's why it's not safer to be depending on the battery, aged battery, okay. So it need to be replaced. So this is what it looks like of manufacturing, operation and reutilization, okay, of the battery. So electrode manufacturing, then cell manufacturing, operational modeling like equivalent circuit modeling that we have seen earlier, or simple ANN based model for state estimation purposes. Lifetime prognosis will be there, okay, fault diagnosis would be there, charging. Then once this operation phase is over, then we will be going for sorting, regrouping, okay, some damaged battery need to be removed. Then echelon utilization means second life utilization, okay, second life utilization will be depending upon the state of health of the batteries. Once it is going below the 80% mark, then definitely need to be considered for the second life uses. Okay, so then material recycling, if after second life it will again go for material recycling, something will be wasted, something will be extracted, then again material preparation and remanufacturing. So this cycle represents the complete manufacturing, operation and reutilization cycle of any battery, any standard battery. Same thing is also depicted over here, like raw material extraction, then material processing, then component manufacturing, cell manufacturing, okay. So then from cell manufacturing it will be assembled into modular assembly, then battery pack will be formed. This represents the battery pack. It will be now assembled into the vehicle through assembly line process. So this is the electric vehicle, and once charging, discharging is done, then it will be used. So once this life is over, first life, then it will be shifted for the second life. Here some off-site, on-site assembly will be there, some stationary power supply use will be there, and the recycling process. Once second life is also over, either it will be wasted for the metal recovery, landfilling, or incineration. It can be directly burnt also, or some recovery can be done like pyrometallurgical, hydro, fire-based, water-based treatment, direct recycling, okay, recovered materials to reuse, recovered components, recovered material for reprocessing. Okay, so this is the complete cycle of the battery life. Now coming to the battery aging in mechanism and types of battery aging. So let us understand the aging of the battery in a detailed manner. Okay, so battery aging is multifactorial, involving electrochemical, thermal and mechanical degradation. So what are the different types? Calendar aging, okay, in calendar aging, degradation during storage, even without cycling. Okay, so calendar aging means even if we are not using the battery, because of just a passage of time, somewhat degradation will be taking place if it is fully charged, and if temperature is continuously changing, okay, time with time. So these are the effects. So calendar aging is like that. Then cyclic aging means because of the usage, charging, discharging cycles, degradation due to the charge and discharge cycles, repeated recycling stress. Okay, so because of that also definitely aging is taking place. Then mechanical aging, expansion, contraction of the electrodes. So continuous electricity is flowing. Okay, ions and anions, cations, they are moving around. So definitely some expansion, contraction, okay, that impact is creating, so physical strains are coming on the material. So because of that also some or the other aging effects will appear. So then thermal aging. Thermal aging means degradation due to overheating. Okay, poor thermal management. So if the battery is continuously exposed to overheating, over temperature, so definitely because of that poor thermal management, it will be having some thermal aging effect. Okay, some components will be lost permanently, their functionality will be degraded. So because of such things, there are 4 types of aging effect, like that is calendar, cyclic, mechanical and thermal aging. Then calendar aging mechanisms occurs when battery is stored or lightly used. Okay, even if it is not in use, okay, definitely some losses will be taking place. Similarly, the main primary cause for the calendar aging is electrolyte decomposition and SEI, that is solid electrolyte interface growth, that is taking place. Okay, it can be accelerated at higher temperature and greater than 80% of the state of charge. I just now mentioned, if the battery is kept full and it is stored at a place, so definitely the degradation will be more as compared to a discharged battery, because a charged battery will have some charge carriers and they will be moving around, so definitely aging effect will be more. So that is also represented here. A lithium ion cell stored at 40 degree with 100% state of charge can lose up to 35% of the capacity in 1 year. Okay, while at 25%, 25 degree and 50% state of charge, loss is only 10%. So see where is 35% loss and where is 10% loss. So this can be taking place. Okay, because of the difference in temperature and difference in state of charge. Okay, initial state of charge. Now cyclic. So now we are going through each and every aging mechanism. So first we covered calendar aging here. Then we are going for cyclic aging. In cyclic aging, because of the charging and discharging cycle, the impact is coming on the batteries to lose the efficiency. Okay, so what are the things that are taking place because of which that degradation is happening is SEA growth, so that layer formation will be there. So electrolyte reduction forms passivation layer. Okay, because of that it will create problem. So consumes lithium ion, capacity fade. Okay, capacity fade. Then lithium plating. Lithium plating is lithium metal deposits on anode during fast charging. So lithium plating means metal deposition on the anode surface. Okay, if it is quickly charged, so it will create some short circuit problem in future. Safety risk is there. Similarly, cathode degradation, transition metal dissolution, reduces active materials. Okay, electrolyte oxidation, high voltage instability, gas formation, swelling. Okay, oxidation means some gases will be coming high voltage because of the higher voltage. Then that gases swelling can be there. Okay, so these are the problems that can take place. Similarly, mechanical stress is there, particle cracking due to volume change. Okay, increasing the resistance. So all these factors comes under the cyclic aging mechanism. So layer growth, platinum deposition, cathode degradation, oxidation because of in voltage instability, then mechanical stress because of the contraction and expansion, volume change of the particles. So cyclic aging is a strongly affected by how quickly we are charging the battery, how much capable it is to completely charge quickly, or how much current it can deliver at a pace. So that those things are the factors which will decide the cyclic aging effect, and how much we are going for depth of discharge. Okay, then similarly operating temperature or depth of discharge means, are we making the battery to go up to 15%, 10%, 5% of the state of charge? Okay, so deeper the depth of charge, so faster degradation it will be. So there is an optimal range between which, so minimum 20% should be the cap. We should not take the battery below 20%. Okay, so otherwise degradation will be faster. And operating temperature, so these things we have seen already. So operating temperature, definitely if higher temperature is there, ambient temperature, of course degradation will be, or aging will be faster. Now this diagram also shows that typical value reduction curve. Okay, an exemplary progression of the residual value throughout the life cycle phase of a battery. Okay, so what happens here? Suppose these are some amount, and here suppose 10, 15, around 12.5 or 12,500 will be here because it is in the middle. So value will be reducing for the first life cycle up to certain duration. Okay, then it will degrade at a faster pace, less than up to this 80% we are able to use this one. Okay, first phase is this one. The battery still has a significant residual value after its first life phase, if it is suitable for second life application. Then from here second life will be there. Remodeling the battery for second life increases the residual value. So this will be for the second life, and here you can see stationary applications are possible. Okay, this is the first page where electric vehicle application. So by the time the battery is shifted to the second life, means almost the value is degraded by 2/3. Okay, suppose this is 12,500, so this value is somewhere near below 5,000. Okay, so definitely almost 2/3 value is lost. Then at the end, once the value is very low, so definitely it has to be shifted for that recycling. Okay, so end of first life, end of second life, almost 20 years, 15 to 20 years. Battery can be lasting for 10 to 12 years. Okay, minimum. So this is all about the exemplary or value reduction inside a battery with passage of time and its different life cycles. Okay, first life and second life cycle. Now coming to the operating temperature. Okay, what are the different factors which will influence the aging effect? So operating temperature already mentioned. Optimal range is between 20 to 40. If it is going below 20, problem is there. If it is going above 40 degrees Celsius, again further problem will be coming. So low temperature, what happens? Lithium plating during charging, and when high temperature, accelerated layer formation. Okay, that solid electrolyte interface growth and electrolyte oxidation will be taking place. The rule of thumb is for every 10-degree rise, degradation rate roughly doubles. Okay, so that this is the basic thumb rule. If the temperature is increasing by 10%, what will happen? The degradation will be double. It will be very much faster. So erroneous behavior. This is also called erroneous behavior. Okay, so first factor is operating temperature. So second factor is state of charge and depth of discharge. So if we are keeping the battery always more state of charge, so greater than 80%, so electrolyte oxidation can take place. If we are keeping it below the 10% mark, deep discharge, then anode degradation will take place. So best storage range of the battery to avoid any kind of aging, means very minimum, bare minimum aging. For that purpose, we need to have the battery kept between 30 to 60% of state of charge. So example can be a battery cycled at 80% depth of discharge last 1000 cycles, while up to 40% if you are degrading, means using the depth of discharge, once it can be reached to 5000 cycles. Means if the battery is not allowed to go below 40%, then definitely it will last almost 3 to 5 times. Okay, as compared to the batteries which are going below the 20% mark, or depth of discharge being at 80%. So this diagram also depicts the complete summary of all the factors involving. So aging factors, time is there, thermal factor, electrical impact, mechanical impact is there, then degradation parameters of the battery, which components will be degraded is shown here. Then degradation mode, so loss of lithium in battery, loss of internal impedance, then loss of active electrolytes. Okay, so let us briefly discuss this also. So thermal impact, high temperature, low temperature, so that is the problem with temperature. And electrical impact, like high cell voltage, okay, high state of charge, load current is more, low voltage is problem, overcharging, discharging is a problem, mechanical pressure, mechanical stress are the different mechanical impact. Now what are the factors here? AC formation. Okay, here you can see this is a separator, here anodic surface is there, here cathodic surface is there. Okay, you can say anode or cathode, and here some blinders are there, and this is aluminum current collector. Okay, and this complete thing is immersed in electrolyte, we can say. So what happens at this layer formation of SEE, the first factor parameter, then copper cracking and contact loss at the this connector point, then SEE deposition, particle cracking, SEE formation, internal short circuit. Okay, at fifth this point it can take place. Aluminium collision and contactless, this can take place here. Then binders decomposition, transition metal dissolutions, lithium plating, then red formation, then graphite exfoliation is there, copper dissolution and then red formation is there. So like this, different problems or factors can be responsible for the degradation of the battery. Now other parameters are, other factors are charge discharge rate. So already mentioned how quickly the battery is able to charge. That also can cause some form of aging. So high C rate, more heat will be there, lithium plating deposition will be there, and of course stress is also there. So fast charging greater than 2C shortens the cycle life by 30 to 40%. So if it is having greater than 2C charging, means if the battery is gets fully charged within half an hour or less than that, so what happens? Smart charging, that life cycle will be degraded or shortened by up to 30 to 40%. So smart charging profiles, multi-stage or pulse charging reduces these stresses. So we should not continuously charge. Some intermittent charging, that is also called pulse charging or multi-stage. So one by one, phase wise, we can charge the battery so that aging effect can be slowed down up to certain extent. Then next is of course mechanical and environmental conditions. Okay, so what happens in mechanical and environmental? Vibrations, humidity effects, the pack interconnects and seal. So mechanical fatigue in the electric vehicles can take place. Okay, depending upon the road condition, accelerates the contact resistance growth. Okay, then material and cell design. So cathode NMC degrades faster than LFP at the high voltages. Okay, cathode means in the nickel, manganese, cobalt, this degrades faster than that lithium iron phosphate at high voltages. Okay, so similarly electrolyte formation, separation thickness, anode coating influence the long term stability. So depending upon the cell design as well as the material used also impact the aging effects. Okay, so that also need to be considered. Okay, so this represents that use phase, end of life, then production. So suppose production will start from here, secondary material quality, scaled plants, origin, okay, raw material origin, battery model, efficiency, lifetime, functional use, and then end of life means it will come a process model, a recovery rate, system model. So this is just a representation of the cycle, life cycle assessment. Okay, LCA means life cycle assessment. Now this diagram also shows the complete process of right from material extraction and processing, component manufacturing, then cell assembly. Once the cells are assembled, modules will be installed in the vehicles and it will be used for transportation. Once the life is completed, it will go for second life usage. Recycling will be done. So different types of recyclings are there, and it will be again tried to be extracting some of the useful materials. Okay, and again get back to the cycle of the battery manufacturing. So complete closed loop can be formed, so that here you can see like pre-treatment, leaching, impurity removal, then precipitation, some form of recycling. Here also similarly HRB will be that type B recycling here, disassembly and discharge, crushing, drying, filtrating, separation, okay, leaching, purification, multiple extraction. So these are all the processes involved in recycling, and the complete life of the battery is depicted over here. The purpose of life cycle modeling, what is the purpose of going for this life cycle modeling? Predict the capacity fade resistance growth and remaining useful life. So this will help to predict the capacity fade, resistance growth, and how much longer we will be able to use the battery. It supports the BMS in decision making for power limits, maintain schedule. So if life cycle modeling is done properly, so how much power it can be allowed to receive, or how much quickly it can deliver certain current. So those decisions that are required to be taken by BMS will be quite helpful. Okay. Then modeling approaches. So how we will be able to do the life cycle modeling? Okay. How we will be able to do the prediction? Okay, of the this capacity, resistance growth, remaining useful life. So there are 4 different approaches of modeling. First one will be empirical, based upon the experimental factors derived from experimental cycle data like capacity loss proportional to exponential of time, okay, function of state of charge, C rate and all. So these are all experimental based. Then electrochemical modeling based upon the chemical reactions, okay, physics involved in that layer formation, reaction kinetics, diffusion impact, okay, pseudo 2-dimensional models can be generated here. Then data driven models are there using AI ML. So learn degradation trends using historical data that can be done. Long short term memory, random forest, which we have seen in the previous lectures, all these things can be used, or any combination of these. Okay, one or more combination of this can be used for hybrid modeling. Combine the electrochemical plus AI based predictions. Okay, physics informed neural network. So physics informed neural network helps in predicting this electrochemical plus data driven. If we are combining these two, we'll definitely going for physics informed neural network. So these are all different types of approaches which can be used to effectively create the life cycle modeling. Okay. Now coming to the key aging indicators. So how we will know that battery has been aged? Okay. So some indicators should be there. So capacity fade is represented as QT with respect to time. How much capacity is remaining? Okay. So Q0 initial condition minus K1 into n number of charging discharging cycles, then K2 into exponential of temperature. Okay, initial temperature or present temperature. Okay, operational temperature. Then internal resistance growth, linear increase with cycle or exponential beyond 80% state of health. Okay, state of health estimation equals to C measured by C rated into 100. So what happens? Internal resistance growth means linear increase with cycling or exponential beyond 80% state of health. Okay, state of health estimation means equals to C measured divided by C rated into 100. So C measured means how much is the present measured capacity, how much was the initial capacity. So that will give us the state of health, which we have already discussed these things. Then remaining useful life means until what we will be able to use the battery so that the it will drop below the 80%. State of health will come below the 80%. So the time duration left or remaining cycles until the capacity drops below this value, 80%. So validation. So how to do the validation? Laboratory cycling test under different temperature, current and depth of discharge profile. So validation can be done using experimentation. Okay, laboratory based forced cycles testing. Then accelerated aging test can be done using Arrhenius based scaling. Okay, these are some mechanisms available for testing related to the aging effect or life cycle assessment. So use of hardware in loop for faster simulation. So these things are available in tools that can be used for going for life cycle modeling and testing. Then what is the role of battery management system in life cycle management strategies? Okay, so battery management system, it will do the real time monitoring of state of health, state of charge and temperatures. Okay, implement adaptive charging, cell balancing and all protection. So these are the functionalities, okay, of BMS, and it will help to predict the analytics for remaining life estimation and maintenance alerts. Okay, so these are the tasks that BMS will do, and from here operational strategies like thermal management. Okay, this will be also done by the BMS. Okay, liquid or air based cooling to maintain the optimal temperature. Smart charging algorithm. So which charging algorithm will be used for maintaining that one? So limit high state of charge, okay, charging, then use constant current slash constant voltage charging. So smart charging algorithm should be used. Like constant current means initially we will be using a constant current and voltage will be gradually increasing, and once the charge is going beyond 80%, constant voltage will be maintained and current will be slowed down. Okay, so that is the CCCV, constant current, constant voltage charging mode. Okay, active balancing can be also used to equalize the cell, like cell balancing that we have learned in the previous lecture. So equalizing the cells to reduce stress on weak cells. Okay, usage optimization can be done. Limit in usage optimization, what needs to be done? Limit depth of discharge. Okay, we should not allow the battery to go below 20%. Okay, so that will extend the battery life cycle. So this diagram also suggests related things, like here intelligent material chain. So proper materials should be selected, full life cycle traceability management and green recycling. Intelligent information chain. So full life cycle data sharing and intelligent management. So here you can see data from the BMS can be extracted to the cloud. Okay, cloud means servers. Then intelligent sensor should be available in the bike. It will share that. So these things can be transferred and this data can be used for battery, retired battery, repair, extended life. Okay, recycling analysis can be done, remanufacturing, regeneration and all. And here from this battery sensors, intelligent disassembly can be done, cell module, intelligent sorting can be done, intelligent regrouping. Okay, different manufacturers batteries can be grouped all together. Okay, different status depending upon the remaining useful life, they can be categorized and grouped. So like that we can be doing some form of recycling or life cycle management of the batteries. Okay. So similar things are also represented here. Battery management system. Okay, BMS operation, how it will be managed. So modeling and state estimation. So here you can see equivalent circuit model that we have seen. So state observers means that state estimators are there to estimate the state of charge, state of power, state of health, remaining useful life, joint states. Okay, remaining capability, energy estimation, power capability prediction, life cycle and health prognosis. Other indexes of the battery, they can be estimated, and here individually cells are connected, monitored. Okay, temperature sensor, voltage sensor. So this is the battery, this is the BMS operation, some communication bus are there. Okay, then here we are in the BMS, we are using these models to estimate these things. So key tasks are, and this BMS is a part in the battery pack, and this is the electric vehicle, low carbon and zero emission transportation. So all these things are interconnected for the sustainable e-mobility. Okay, so data acquisition, operational modeling, state estimation, lifetime prognostics, fault diagnostic and alarm, battery charging, communication, all these are the various components involved in this task. Okay, now end of life and second life management. So what happens once the battery is going to cover its, or it has already performed the first life cycle. So EV batteries typically reach end of life at 80% of the capacity. So second life already mentioned, stationary energy storage. Okay, solar microgrids we can go for, peak shaving or UPS uninterrupted power supply for the computers, or ventilator, some critical loads we can supply. Telecom backup power is there. Then example here, example can be a 60 watt hour electric pack, EV pack, after 8 years retain 48 kilowatt hour usability capacity. Suppose 60 watt, it is almost losing 20% of this one, can serve for after 8 years, still it can be used for residential solar backup, and where it can last up to another 5 to 7 years. So combinedly you can see 8 plus 5 or 7, almost 13 to 15 years is the minimum work life of the battery, combining the first life and the second life. Then recycling and circular economy. So recover lithium, nickel, cobalt, copper, whatever are used And recycling techniques we have already seen fire-based, pyrometallurgical smelting, hydrometallurgical, chemical leaching, direct recycling can also be done. Okay. Then sustainability goals. So reduce raw material extraction and manufacturing emissions. This can be helpful in achieving the sustainability goals. So here mining, refining, material generation, battery management, manufacturing, battery user, second life use. Okay. Landfilling. So here every point we can do some recycling. Okay, pre-treatment, material extraction, then pre-treatment it can come for hydro based recycling. Then here we can come for pyrometallurgical recycling, fire based. So these are the complete life cycle assessment and recycling process involved. So with this we are coming to the end of this lecture. So what are the summary points or conclusion that we can draw is, so battery aging is a complex process driven by thermal, electrochemical and mechanical stress. Okay. Life cycle prediction models enable proactive BMS decision. So if we are able to do the life cycle modeling, it will be helping us to take better decision on behalf of the BMS. Okay, the BMS operational efficiency will be improved. Further, thermal management, smart charging, balancing can extend the life of the electric vehicles. Okay, can be extended by 30%. End of life batteries can be repurposed. End of life batteries can be repurposed for stationary storage and recycling. Contributes to sustainability. Okay, end of life batteries can be repurposed for stationary storage and recycling contributes to sustainability. So discussion questions that we can analyze are, why does high state of charge accelerate the calendar aging? Okay, at the beginning I told that higher the state of charge or the capacity in the battery, that degradation will be more. So because of the available charge carriers and all. Okay, compare the empirical and AI based aging modeling. This can be analyzed, which will be more suitable for electric vehicles. So how can life cycle management contribute to reducing the electric vehicle cost and environmental footprint? Okay, so these things we can discuss, or those audience who are interested further, they can explore. And with this we are completing this lecture, and thank you.